los científicos más importantes del mundo entero. He's one of the most important scientists of the world.
Don't translate.
Le plus important scientifique. He was born in Casablanca, then moved to Paris, where he studied, and got his PhD under the supervision of another master of quantum physics, Claude Cohen-Danucci. So Claude is a member of a dynasty of Nobel laureates. He was awarded with the Nobel Prize in 2012 for the creation and development of methods to manipulate individual quantum systems. That is part of the work that changed some of the ways we think about quantum physics nowadays, and the work that Serge and his group did in Paris at the École Normale Supérieure at the beginning, and then I'm skipping the fact that he was a postdoc in many prestigious places in Yale and everything, but he was a professor at the École Normale Supérieure in Paris, where he did some amazing experiments that were the basis of the Nobel Prize that he received in 2012. When he, at that time, he was moving to the Collège de France, one of the most prestigious institutions in France. He was president of the Collège de France for several years, and he visited Argentina. He's a friend of this house of our country, of Latin America, and science in general in the I don't know how to say it, in the developing world or the underdeveloping world, or the world that is becoming more and more underdeveloped. So Serge is a friend of the house, and is a friend of good science all over the world. He's one of the 69 Nobel laureates that in March or April last year signed a letter expressing their concern about the situation of science in Argentina. 69 Nobel laureates signed that letter. Our government couldn't care less about that and didn't do anything to improve the situation of science. So thank you, sir, for coming, and I'm looking forward to listening to your talk about the laser in quantum science.
Thank you, Juan Pablo, for your warm welcome. As you have said, I have been here many times, and I always enjoy to come back here. One of the reasons is a good sense of humor that I find it anywhere in Argentina, and must say anywhere in South America, so I love to visit there. And I will tell you in my talk that there are some very important breakthroughs in science which were made in South America, and which are not directly related to the laser, but I think it's interesting to notice that. So, as you know, we are celebrating this year the 100th anniversary of quantum physics. This physics was, in fact, this discovery was made in 1925, exactly 100 years ago, and among all, of course, this has opened a lot of invention, has made possible a lot of inventions which use knowledge that we have learned about the way atoms and photons behave in the microscopic world. But one of the most useful tools which has come out of this quantum revolution is, of course, the laser. And I think this goes two ways. First, the laser is an offspring of quantum physics. It has been discovered after it has been invented after many discoveries about the interaction of light with matter, and I will come back to that. And once the laser had been invented, it has become a very powerful tool to get deeper and deeper into the laws of quantum physics. So I will talk to you about this story in this talk. I will try to recall all the sequence of discoveries which have led to the birth of the laser, which I like to call tame the light as opposed to the chaotic light that we have from ordinary sources. And I will describe some of the breakthrough that the laser has made possible in basic science. Of course, we all know that there have been a lot of application of laser in applied sciences, but I will restrict myself to basic science, and I will maybe discuss what it holds for further discoveries in basic science in the future. So the outline of the talk is quite simple. In the first part, I will talk about the pre-laser area, how quantum physics has prepared the scene for the laser to emerge, and then I will talk about what the laser has made possible since 1960. Of course, we know that the story has started before 1925, and there have been something like 25 years, a quarter of a century, which we call the period of the old quantum theory, in which many basic discoveries about light and matter have emerged. We have to, of course, to talk about Planck and Einstein, 1900 and 1905. Planck, in fact, was able to find the distribution of frequencies of the black body radiation, of the thermal radiation, by assuming that the exchange of energy between light and matter occurred in discrete quanta, and he introduced for that what is known as a Planck constant, which is a unit of action, very small unit of action, and the quantum of light being the product of this constant with the frequency of the light. And then 5 years later, Einstein went even deeper by assuming that light was in fact made of photons, with the discrete photons, and this allowed him to explain the photoelectric effect. Then, a few years later, Niels Bohr was the first one to use the Planck constant to understand the structure of atoms, that he was able to describe the energy levels of a hydrogen atom by quantizing the orbits using Planck's constant as a unit of angular momentum for doing that. And of course, he explained this way why the atomic spectra are made of discrete lines. So this was really a big discovery, which was followed 3 years later, again by very important work of Einstein. Einstein used Bohr's model to try to recover, to demonstrate in another way the black body radiation formula by making the balance between the energy that an atom was absorbing or emitting into the light field. And he found that in order to recover Planck's Planck formula, he had to admit that there was 3 processes by which atoms interacted with light: absorption, spontaneous emission, which was described by Niels Bohr, but also stimulated emission, meaning that if a photon was impinging on an excited atom, the atom was induced to emit a photon identical to the impinging photon, which is a process of amplification, which we know is essential for the laser to work. So this, and also around 1916, this was the first hint that the photons were undistinguishable particles, because the photons which are added by stimulated emission are identical to the photons which are already there. It's impossible to distinguish them from each other. And this idea that the photons are indistinguishable, which is a quantum property, was reinforced in Einstein's mind a few years later when he received a letter from an unknown young Indian physicist, Bose, who had recovered again the Planck distribution of frequencies in thermal radiation by assuming that the photon was the light which was inside a box which was painted by atoms. This light was in fact like a gas of particles, gas of photons, but in order to count the state, he assumed that the configuration in which photons were exchanged between different states were only one configuration, which means that you cannot assign a number to the photons as Boltzmann used to do when he described the distribution of atoms in a classical gas. So this reinforced the idea that the photons were undistinguishable, and Einstein went one point further. He assumed that some atoms, which were later called bosons, should behave in the same way as photons, be undistinguishable, and this led, according to what the calculation that Einstein made, at a very low temperature to what's known as Bose-Einstein condensation. All the atoms would fall in the same quantum state. At that time, it appeared very strange, and it was supposed to be just a kind of theoretical consideration without any application. And of course, we know that 70 years later, it led using lasers to be observed. It's called the Bose-Einstein condensation. So at that point, the situation was ripe for a big leap forward. And in 1924, this is the last step I will discuss here, of the pre-quantum era, Einstein received the thesis of Louis de Broglie, who was a student of Langevin. Langevin was a good friend of Einstein, and Langevin did not know what to do with this. It was a very revolutionary idea. De Broglie made the assumption that particles, electrons, behave also as waves. So he extended what Einstein and Planck had done in 1900, assuming that light, which has always been considered as a wave, was made of particles. He takes the opposite point of view, saying that particles, like electrons, had also a wave-like character. And immediately this idea pleased Einstein, and he wrote to Langevin a famous sentence that your student has lifted the veil which is hiding the mysteries of the quantum world. And lo and behold, a few months later, this was revealed by Schrödinger and Heisenberg, and this is a famous year 1925. Schrödinger found the equation which describes the evolution of the Broglie wave, and this was the birth of wave mechanics with this famous Schrödinger's equation. And independently, and in fact a few months before, Heisenberg had given a completely different description of quantum physics, associating to each observable, each physical quantity, a matrix, a set of numbers, and the matrices do not commute, which means that if you measure, for instance, the position and then the momentum of a particle, you don't get the same result as if you do it in the opposite way, measuring first the momentum and then the position, and this leads to the famous non-commutation of position and momentum, which again involve Planck's constant. These 2 points of view at the beginning were supposed to be quite at odds with each other, but then very quickly it has been demonstrated that there were two expressing the same physics in two different languages. And in fact this happened between June 1925 and then December or January 1926. And during the period that were exactly 100 years after, in October, November of 1925, there was a lot of people getting interested into that. Born and wrote a paper with Heisenberg and Jordan, and they put all this into a very consistent framework, which was completed by Schrödinger's point of view. So all the setting was ready to understand in depth how atoms interacted between themselves and interacted with light. And the last discovery I want to stress in this period, in fact, predated by a couple of years, 1922. It was not a theoretical breakthrough, but it was an experiment. It's the experiment by which Stern and Gerlach measured for the first time the magnetic moment of atoms. The idea they had was very simple. We know that atoms and matter present some magnetic properties, and since Ampere in the 19th century, it was assumed that this was due to electrical currents inside molecules and atoms, and the question was, how big is this magnetic moment? And so they designed the experiments that you can see here. You have a furnace which you heat the furnace with silver atoms in it. It makes a beam of silver effusing in vacuum. It's called an atomic beam. And these atoms are going in the gap of a very powerful electromagnet which supply a gradient of magnetic field along the vertical direction. And this gradient of magnetic field exerts a force on the magnetic moment of the atom. And the idea was simple: by measuring the deflection and knowing the gradient, we know what is the magnetic moment. What they expected to see was a continuous trace, because classically the projection of the magnetic moment along the direction of the gradient could vary continuously, and they were very much surprised to find instead a double spot. In fact, what they had discovered by this experiment is what we know now as the electron spin. The magnetic moment is associated to an intrinsic angular momentum of the electron, which is spinning on itself, so to speak, and this momentum, this magnetic moment, can take only two values when you measure it along the vertical direction. This is known as spin up and spin down states. And this spin is, of course, an intrinsic property of the electron, of the valence electron in the cellular atom. So this setup will separate the magnetic moment. It shows what has been called spatial quantization, and the existence, the first proof that there were two-level systems in quantum physics, spin up and spin down, and for example, all the modern quantum information theory and experiments we are doing now are based on exploiting the properties of these two-level systems. So you can think that about this spin up and spin down set as the future qubits that everybody is talking about, especially in the context of quantum computer and quantum information. And I show you here the signal that they observe. You see the splitting trace. It's just the super atom which are deposited on a piece of glass downstream. It's a kind of double leap, and they join in the end because if you go away from the axis of symmetry, the gradient of magnetic field decreases, so the splitting goes down to zero on the left and the right. And they had the intuition that they had made a great discovery, and in fact, they immediately put this signal on a postcard, and they sent the postcard to Niels Bohr in Copenhagen, because Niels Bohr was the first one to have quantized the angular momentum. In fact, Niels Bohr have quantized the orbital momentum, and what they were observing is the intrinsic momentum. So it's in fact a confusion. It's a little bit like confusing the day and the year in the motion of the Earth around the Sun. But still, it was the first proof that the angular momentum was indeed quantized. And so they wrote in German, "We congratulate you for the confirmation of your theory." So it was not an exact confirmation, but still it was a great point. In fact, I took this picture from the Niels Bohr archives, and if you look at the other side, it's of course the address of this postcard, and they had written Professor Bohr, Copenhagen, and that was enough in 1922 for the postcard to arrive to his recipient. So what I want to say is that this simple split trace on the glass plate announces the 20th century quantum revolution in technology, that I will tell you in a moment, and the qubit in the 21st century. But of course, many other steps had to be taken, and the next step, the next thing I would like to talk to you about are the result of the very beautiful experiment which Isidore Rabi did at Columbia University at the end of the 20s, beginning of the 30s. In fact, Columbia, Rabi had come to Europe, to Hamburg, to be a postdoc of Stern. It was a time when people were traveling from America to Europe to gain knowledge, and things have changed, and maybe they are changing again now. So that you see what happened at that time. Rabi started a very productive group in Colombia, and they did very, very important discoveries. In fact, what Rabi did was to try to extend Stern's work, not to measure the electronic spin, but the nuclear spin, the magnetic moment of nuclei. They are much higher, which means that they have much smaller magnetic moments, so you need much higher field gradients and improved setup. And you see that you want to separate the spin up and the spin down state in a magnetic field, and show you here the two levels and the two energy levels that you can represent in this way. And the setup they use was a kind of improvement on Stern's setup. And now, instead of having one electromagnet, they have two electromagnets A and B, which apply opposite gradients to the atoms or molecules, so that the atoms and molecules are pushed up in the first zone A and then pushed down in the second one, and so they follow an S-shaped curve, and they're focused on a hot wire at the right of this slide. On the hot wire, the molecules deposit electrons, giving rise to a current, and this current is proportional to the flux of particles which reach the wire. The important addition is the cavity that you see in zone C between A and B. In this cavity, a radio frequency field is applied to switch the spin from up to down. If the frequency of the photon is such that h nu value, h is Planck constant, is equal to the energy difference, then the spin will absorb or emit radiation, go from one level to the other, and if they do that, they will no longer be focused in a certain zone, and so the signal will decrease. The signal that the hot wire detects will decrease, and you see the first signal which was detected in 1939. This is the first magnetic resonance signal. You see a decrease in the signal when you reach resonance, and by measuring the frequency of this resonance, or by scanning, for example, for a given magnetic field, scanning the frequency, they were able to find the magnetic moment of various elements, hydrogen, but also deuterium and all kinds of chlorine and many atoms and molecules. And this was really a breakthrough. And this first magnetic resonance announced, as I will show you now, NMR, the MRI, that is magnetic resonance imaging, atomic clocks, the GPS, optical pumping, the maser and the laser. And many discoveries have been made then in the 1930s, the 1940s and 50s, leading progressively to the laser. And Rabi was very, a lot of imagination and a lot of, had a very deep way to look into the future, and he was reported, he gave a conference in Columbus, in Ohio, at a meeting of the American Association for the Advancement of Science, and one journalist who attended the lecture wrote this headline: "We are all radio stations, Columbia scientist reports, all atoms in humans or in steel found to emit and receive long waves." So Rabi must have said that the atoms that we have in our body behave as the atoms in the atomic beam, and if you apply a radio frequency field at the right frequencies, they will emit and absorb radio waves, which will go out and propagate information outside. So he was, I don't know if he thought about MRI, but basically this is something which we, after a lot of progress, lead to magnetic resonance imaging. In fact, for that you have to make, of course, many progresses. It's not possible, you cannot detect the molecules in your body by just having them in vacuum and detecting them on the hot wires. It's a destructive method. If you want to extend this, what you have to do is to have a non-invasive, non-perturbing way of detecting the atoms in a solid or in a liquid, and this is what was discovered by Purcell and Bound in 1946, and in fact they were able to detect NMR not on in a tenuous atomic beam, but in bulk materials, liquids and solid. The idea was to excite this resonance and to have antennas, to have coils around which detect the microwave, and as you tune the microwave, you see resonances which give you information about the chemical nature or the atomic nature of the medium that you are investigating. I must say that this has made possible because the radio sources have made great progresses during the war. In fact, a person was working in MIT in the lab which developed the radars, and so he had gained the expertise which made these experiments possible. And after a lot of work, it led, of course, 30 years later to the magnetic resonance imaging that we know plays a very important role in medical diagnosis and a lot of biological studies. In the same way, Rabi had also the premonition of atomic clocks. In fact, when they were working in the 1950s, what they discovered is that the ground state of alkali atoms is a two-level system. If the spin of the electron and the spin of the nucleus are parallel, the energy is different from what value it takes if the spins are anti-parallel. And this two-level structure, it's called the hydrogen structure. And for example, in cesium, it falls at a frequency of about 9.2 gigahertz. And so it's possible to excite this transition, and this is the basis of the microwave atomic clock. And the design of the clock was invented by Norman Ramsey, who was here, he's old, but he was at the time was a student of Rabi. And he improved the setup of Stern and Rabi by splitting the microwave zone into two spatially distinct zones. So the atoms were submitted to a first pulse of microwave in the first zone and to a pulse in the second zone. And according to quantum physics, this gives rise to a quantum interference effect. And when you scan the frequency, instead of having a single resonance, you get fringes, narrow fringes, which are due to this, to the fact that the amplitude for the spin to switch in the first zone and the amplitude for the spin to switch in the second zone interfere with each other. And depending on the phase difference, give rise to maxima or minima. And the advantage is now that you have a very narrow structure. The central fringe is very narrow. And if you look the microwave to the center of this fringe, you get a very stable and a very precise source of microwave. And again, after many years of improvement, this led to the microwave clock. And these clocks are now embarked in satellites, and by the signals they send to our cell phones, we get our position everywhere on Earth with a precision of 1 or 2 meters. So it's very important for navigation, and this is possible because this clock have an uncertainty of about 1 nanosecond, 1 billionth of a second per day. And if you compare that to an ordinary pendulum, an ordinary pendulum has a period of about 1 second. Here we are 10 orders of magnitude higher in frequency, and the stability is 10 orders of magnitude bigger. That explains why you have now 1 nanosecond of uncertainty instead of a few seconds that you have for mechanical pendulum. So this was also a very important advance. Another predecessor invention is what is done as optical pumping, and this brings us closer to what my own field in this physics. Alfred Castel and Jean Rossel, who were working at École Normale Supérieure in the 1950s, invented a way to orient the magnetic moments of atoms in a way very different from the Stern-Gerlach method. Instead of applying a gradient of macroscopic field, what they made is to let the atom interact with polarized light. It's basically the same interaction. It's electromagnetic field interacting with atoms, but it's a very, of course, different physical process, and they were able in this way to exchange angular momentum between light and matter, making matter absorb the angular momentum of photons, and this is the basis of optical pumping. It was done with classical light, it was before the laser. And Kastler, when he predicted this effect, also noted that this could be a way to cool atoms, because if you bring all the atoms into the lower state, you get a distribution, a thermal distribution at a lower temperature. So he calls that the effet lumineux frigorifique, light cooling effect, but he said this would be just a footnote, it would never be important. So he was very modest because it was the basis, it became the basis of the laser cooling much later. Castor and Brossel had a student, Claude Cohen-Tanucci, that you see here in 1960, and Claude Cohen-Tanucci made the theory of optical pumping, and by writing his equation, he discovered something new. He discovered that if light is not resonant with atomic transition, it cannot be absorbed or emitted, but it can shift slightly the energy levels of the atoms. This is called the light shift effect. At that time, it was a very small effect. The shifts were about 1 Hertz, and they were observed because of the extreme sensitivity of optical pumping. But now, with laser, we make light shifts of gigahertz, and if you focus light on the atoms, this shift depends on position, because it depends on intensity, and much larger, of course, when you have a high intensity than a small one. And the gradient of this shift is a force which is very important, and this is a kind of force which allows us to trap atoms or to cool atoms in laser light. So it was a very important step. And also, this shift give a way to measure, to count photons without destroying the photons, because the photons cannot be absorbed, but still they perturb the energy levels of the atoms, and if the atoms are very sensitive, they will be sensitive to single photons, and I will come back to this a little bit later. So you see, this is about the kind of the stage that light-matter interaction had reached in 1960, and this is the point when the laser came on the scene. And this brings us back to Columbia University. You see here on this picture Charles Towns and his student Gordon in 1954. Towns was a young colleague of Raleigh at Columbia. He didn't make his thesis with Raleigh, but he was a young colleague. And you see them in front of an ammonia beam, ammonia molecular beam machine. And this was the machine with which they observed the laser effect for the first time. In fact, the ammonia molecule is a two-level system. The formula is NH3, so you have 3 hydrogen atoms in a plane, and then nitrogen atom either on one side or on the other side. And the nitrogen can go across the plane by tunneling and oscillate, brings an oscillation to the system. And in fact, the eigenstate are the symmetric and antisymmetric superposition of these two states, so it's again a two-level system. And if you're able, as they did, to prepare the atom by a gradient of electric fields to be in the upper state, and have this molecule enter into a cavity which is tuned to the transition frequency, it will deliver photons which will be amplified in the process, and it will be the first source. It was the first source of coherent microwave produced by stimulated emission of radiation, and they use the acronym MASER to describe this. And of course, from then on, it became very interesting to go to the laser to replace the N of microwave by the L for light, and it took a couple of years. In fact, Towns thought at the beginning that optical pumping would be a good way to prepare the atoms in the upper, or the molecule in the upper state. And so he went to Paris to work with Kastler and Brossel for a while. This was before I joined this lab, but this was not the right way to do it. And in fact, the first laser optical amplifier was invented by Theodore Maiman, who used a quite different process to get population inversion. I don't have time to get into the detail. And the laser was born. So in 1960, and of course, this was a revolution in optics. It's really a tool which has completely changed the role of the game in optics, and this will lead me now to the second part of the talk, which is to talk about what we have done with the laser since then. On the first slide, I will just summarize a few properties of laser light. As I said, stained light, instead of having all the atoms in the source to emit independently chaotic light, which has a different intensity in different direction and different frequencies and so on. Now all the atoms emit in step, in the same mode of the field, ideally, and you get a beam of intense, directed, monochromatic, and coherent radiation. And I can tell you that in the 1960s, when we saw the first laser in the lab, it was really amazing. Now it's very familiar. You see this kind of signal, but to show that in 1960 was quite something different. So just to summarize, first of all, what you get due to the intensity of this radiation. If you focus the laser light on a piece of solid, you can get such high temperature that it can evaporate the solid, transform it into plasma, reach the temperatures that you have inside stars, millions of degrees. You can even ignite fusion reactions. And you can also do the opposite. If you shine light on the atom in different direction, you can have light absorb the momentum of the photons in such a way that you can cool the atoms to the lowest temperature you can think of, billions nano-Kelvin, 10⁻⁹ Kelvin can be reached fairly easily. And at this very low temperature, the double wavelength becomes very large. The double wavelengths of different atoms overlap, and you fall into the Bose-Einstein condensation with bosons and into similar non-classical effect with fermions. So this is a very important field, which is basically due to the high intensity that you can reach with laser light. Now, another kind of applications come from the fact that this is also can be a very stable light beams, which oscillate without skipping a bit over millions of kilometers. You could, in principle, reflect a laser beam from the moon, and the beam which comes back is in phase with the emerging beam. You can have very long-based interferometers. You can also, if you make the laser emit on well-defined frequency separated by a fixed interval, it's called a laser cone, you can, by interference, build up a huge intensity at some point, which goes to zero and comes back later. So you can reach very high power during a brief amount of time, and this time can become very short. In fact, you can now have laser pulses which last a few attoseconds. An attosecond is 1/1000th of a billionth of a second, 10⁻18 seconds. And this is a very powerful tool to make stroboscopic studies of very fast processes in solid and in solid and condensed matter. So to summarize, this gives us a really fundamental tool to do fundamental research in physics, in chemistry, and biology. And I will give you a few examples. But just to recall this period, 1960s, I show you here a picture which was taken in the lab of Kastler and Russell in October of '66, when Kastler got the Nobel Prize in Physics for optical pumping. So you see Claude Cohen-Tanucci, who was my thesis advisor, Alfred Kastler and Jean Russell was working with him, and I am also in the picture, which I think I cannot be recognized. It's even it was taken even much before the picture which was used for the poster of this event, but I wanted to show you how I looked in 1966. And at that time, I discussed a lot with Claude Cohen-Tanucci about what we could do with lasers. So we imagined a lot of things, but I must tell you that we are very, very far from being aware of all what could happen. And I will just give you on the next slide some orders of magnitude. I compare on this slide what we could do 65 years ago in physics and what we can do now due to what we can do with lasers. So the laser has made tremendous progress. It's possible and it has led to quantitative and qualitative evolutions in basic research. And we'll take a few directions. And what I want to show is that more than 10 orders of magnitude improvement have been achieved in many fields. 10 orders of magnitude means, over 60 years, means a factor of 10 every 5 years. And 5 years, it's about the duration of a PhD. So you see that in quantum optics, the evolution is so fast that between the beginning and the end of the PhD, the student has to learn, in fact, quite new technology and has opened to him or to her a whole range of new possibilities. Let's look first of the temperatures and kinetic energy of atoms. In 1960, even cold atoms in the cryostat, you could reach temperature of about 1 Kelvin. Maybe if you use dilution, cryostat maybe a few millikelvins. Now we can go into nanokelvin or even less with laser cooling. So it's a huge gap, and it has led to a lot of possibilities. In other directions, the precision of spectroscopy and clocks. In 1960, the most precise measurement you could make, for example, measuring the Rydberg constant, you could give the value of the Rydberg constant with 8 digits. Now you can give frequencies of some atoms used for atomic clock with 19 or 20 digits. Again, it's a huge improvement, and it has followed the improvement of clocks. In 1960, a clock had a precision, had an uncertainty of 1 part in 10 to the 8, which is about, let's say, 1 second per year, which is supposed to be very good. Now we are talking about 1 femtosecond per day, which is, of course, a huge improvement, and we'll see what it can lead to. The sensitivity of measurements in an optical cell, optical pumping cell, we had billions of atoms, and so what the signal you saw was a statistical average over the atomic processes occurring in big samples. So you could not see quantum jumps, we could not see entanglement, because all this was washed out by statistical effects. Now we can observe a single atom interacting with a single photon, and you can observe all these non-classical features, and of course this has led to the science of quantum information. I will say a few words about the speed and time resolution. Even the fastest sparks you could get at that time were duration of microseconds, maybe nanoseconds. Now we have reached the regime of attoseconds. And I like to think about an attosecond because the second, which is the time scale that we have in our body, because the heart rate is about 1 period per second, it's just halfway on the logarithmic scale between the attosecond, 10 minus 18 seconds, and 10 plus 18 seconds, which is the age of the universe. So we are just in the middle between the age of the universe and the kind of resolution we can reach now with laser, which is the attosecond scale. The last point I would like to make is the sensitivity to length variations. In an interferometer back in the 1960s, we used Michelson interferometers to define the meter. The meter was an integral number of wavelengths, and the precision was about 1 part in 10 to the 8, which is already very good. 10 minus 8 meter, it's a very small fraction of a micron, it's a millimicron. Now, with the interferometers that you have in the LIGO and Virgo gravitational wave antennas, you reach 10 minus 21 to 10 minus 22 sensitivity to length variations, and this is of course a huge improvement. And I will start by just recalling you this experiment, which was the first detection of gravitational waves back about 10 years ago. It was a coalescence of 2 black holes, which were in the last phase of their life revolving around each other, and then collapsing and giving rise during the last second to this pulse of gravitational wave, which were detected by a change, by the imbalance between the 2 arms of this interferometer. And you see here 2 red and blue signals because you had to detect in coincidence what happened in two antennas, just to be able to make sure that it comes from outside and not a noise or some kind of spurious effect due to a mechanical vibration somewhere. So this was produced by these two black holes, and the light has traveled more than 1 billion years. Now think of the amount of energy which was released there. When the two black holes merge, 5 or 6 solar masses disappeared in 1 second. And look at what happened for the sun. The sun is dissipating about 1 part in 1,000 of its mass due to nuclear reaction, so 1,000th of one nuclear mass over 5 billion years. Here we are talking about a mass loss which is 5,000 or 6,000 times bigger just in 1 second. So it's a huge cataclysmic phenomenon, and yet when it reached the Earth, the difference in the length of the two arms of the interferometer is a tiny, tiny fraction of the size of an atom. In fact, this sensitivity 10⁻21 it's a relative displacement in the two arms, which is less than 10 billionths of an atomic diameter. And the system is sensitive enough, and the stability of the laser is big enough so that this has been detected. So this is really the tour de force, maybe one of the most precise experiment, most sensitive experiment ever done. I would like to say in a few words that this experiment is also very interesting in the history of science because it put Einstein's physics between two Michelson experiments. In fact, you all know that the special theory of relativity comes from the fact that the velocity of light does not depend on the observer. And at the end of the 19th century, Michelson had tried to measure how the velocity of light varies depending on whether it propagates along the velocity of the Earth on its orbit or in an orthogonal direction. And for that, he built this interferometer was floating on a pool of mercury, and he was rotating this thing and tried to see a difference in the interference pattern, and he never saw any difference. And it was very puzzling, and this was explained by Einstein when he said, in fact, the velocity of light does not depend on the observer. It's the same for all observers in relative motion with respect to each other. And you see that these fringes could not be displaced, and in fact the sensitivity to fringe shift was about 1/10 of a wavelength. It was very good at that time, it was 1/10 of a wavelength. 130 years later, another Michelson experiment, which is the one I described to you, gave a positive result and detected the gravitational waves, which is one proof of the general theory of relativity of Einstein. And you see that the sensitivity which was required for that was about 10⁻12 wavelengths. That is a huge improvement in precision, and now you have a positive result. I also insist on that experiment because this is the first experiment, I think, which put the United States at the forefront of science in experimental physics. Michelson got a Nobel Prize later for that, and it was a time when the science was mostly in Europe, but this was really the first great experimental result in the United States. 125 years later, unfortunately, we see a regression in the influence of the United States, and I just want, in connection with this experiment, I would like to show you what was the headline in the New York Times a few weeks ago. With scientific discoveries and dreams in the balance, and say research breakthrough are often sagas of passion, curiosity, and sacrifice. And if Trump's proposed budget cuts for 2026 are enacted, many such journeys may never get started. And say in a budget released on Friday, the administration proposed to cut the budget for the LIDO gravity wave detectors by half. The rationale is why two antennas? One is enough, so we can cut the budget by half. So this, of course, is ridiculous, first of all, because you need at least 2 antennas to make sure that you are not detecting express signal, and you need 3 antennas, in fact, and there is a third one, Virgo, in Europe, if you want to be able, by triangulation, to know from where the signal is coming. So this is just a lack of knowledge, but it's just, it makes all the money spent just wasted if you follow this kind of decisions. So now a few words about laser cooling. You see here on this picture counter-propagating light beams on the cloud of sodium atoms which fluoresce very brightly at the intersection. And this, here you have about 1 billion atoms. It's what is known as an optical molasses. They fluoresce and they are at a temperature of about 1 microkelvin, very, very cold atoms. And in fact, the process by which the light is cooling the atom is rather, in this case, rather complex. It's due to the fact that you have in the ground state a hyperfine structure, 2 levels in the ground state of these sodium atoms. And what happens is that the laser beam interfere with each other, and it gives rise to modulation in the light intensity, which is related to a modulation of the light shifts. The light is not exactly resonant, so there is a light shift and the atoms are moving up and down in a landscape of hills and valleys as the light interferes. And the process is such that when the atoms come to the maximum of a potential hill, by optical pumping they are brought down to the minimum corresponding to the other hyperfine state. So there is a competition between light shifts. There is, in fact, a collaboration, in fact, between the effect of light shift and the effect of optical pumping, which makes all the atoms all the time keep raising along slopes, and when they reach the top of the slopes, they are brought in a valley and have to do it again. So Claude Cohen-Tanucci and his student Jean Dalibert call this Sisyphus cooling, to recall the character of the mythology which was condemned to have to go up with a very heavy weight, to keep going up hills before being brought down to the basis. And so this is how you get this very low temperature, and by adding evaporative cooling, you can reach the Bose-Einstein condensation, and then the atoms behave like waves. And you see here what happens if you have a Bose-Einstein condensate and let the atom escape. They escape in a coherent beam of matter, which is quite analogous to a coherent beam of light. So it's kind of atom lasers are now tools for a lot of interesting interferometric experiments and to achieve tasks which were supposed to be impossible before. Optical atomic clocks. Now, you see here very simple schematics of a strontium clock. You have a 3-dimensional or a 2-dimensional, depending on the configuration, crystal of cold atoms. The atoms are held by laser beams to be motionless to avoid Doppler effect. And these atoms are interrogated by a very stable laser, and the laser is locked at the center of the atomic line. The frequency is now in the optical domain 5 orders of magnitude bigger than the microwave clocks of the GPS, and the precision is 5 orders of magnitude higher. So we are no longer at the range of nanoseconds per day, we are now in the range of femtoseconds per day. Femtosecond per day is about a tenth of a second over the age of the universe. It means that if you had started synchronized 2 clocks 14 billion years ago, they would not differ from each other by more than a tenth of a second today. So it's a really huge precision, and these clocks are sensitive to general relativity space-time curvature over a distance of about 1 millimeter. It means that if you move the clock up and down in the gravitational field of the Earth, the beating of the clock will be different, will difference of altitude of 1 millimeter. This kind of effect, of course, is very important. In the GPS, the clocks, microwave clocks, are about 6,000 kilometers above ground, and the correction is 38 microseconds per day, which is very important, has to be taken into account, otherwise the GPS would be completely wrong. But now we're not talking about 30 microseconds for 6,000 kilometers, we're talking about something that you can detect over 1 millimeter. So this illustrates the kind of soft clocks that Salvador Dali painted back in the 1920s. I want to emphasize the fact that you need to use 4 laser systems to exploit all important properties of laser. You need lasers to cool the strontium atoms. You need other lasers to trap the atoms in the optical lattice to have them motionless and far apart from each other. You need a very stable laser to interrogate the strontium transition and to block it to the maximum transition. And finally, you need another laser called the frequency comb, which oscillates at a lot of equidistant frequencies in such a way that the beating between 2 adjacent modes is an exact divider of the laser frequency. And so it's an escape mechanism which transfers the stability of the optical clock down to the microwave domain where you can measure it and count it with electronic devices. So it's really a use of lasers in all the qualities that laser can have. And the people who are doing that, especially the Johnny E, who is working in Boulder, are trying to get to even more precise clocks by going, for example, to nuclear clocks, or by using entanglement, by entangling the atoms which are inside this crystal in order to increase the precision and the sensitivity of the measurement. So this is not the end of this adventure. A few words about the use of lasers to make non-destructive single atoms or molecules, manipulation with lasers. I show you again here this picture of Kastler holding a cell with about 10 to the 13 and 10 to the 14 mercury atoms. Now you can work with a system in which the atoms can be seen one by one. You see here a kind of a string of 54 calcium ions, atoms which have lost an electron, which are held along a chain by using the gradient of produced by electrodes. So it's again kind of Stern-Gerlach experiment at a different scale. Each atom is fluorescent when a laser beam is focused on it. And you see here a white beam which is focused on the 54 atoms. Each atom can be interrogated individually with a focused laser beam. It fluoresces in one state, and in another state it is dark, so it's a qubit, and you can prepare it in superposition. You can entangle 2 of the qubits along the chain in a deterministic way, and it is one of the kind of systems that can be used to demonstrate elementary steps of quantum computing. So this experiment was done in particular by Dave Wyman in Boulder. In Paris, we did the opposite. Instead of using light to manipulate atoms, we used atoms to manipulate light, to manipulate microwave in a cavity. So you see here a setup, which is again a Ramsey setup. You have a cavity which contains 1 or 2 photons, or a few photons, and this cavity is sandwiched between 2 zones, R1 and R2, when you can apply separated oscillatory field. Prepare a superposition of atoms in one state and then detect it by applying another pulse downstream. And the atoms that we are using are Rydberg atoms, very excited atoms, which are very sensitive to microwaves. And in this experiment, we detune slightly the cavity from the resonance so that the atoms cannot absorb or emit microwave photons, but the energy levels are shifted by the interaction. And the system, the Rydberg atoms are so sensitive that in fact the fringe, Ramsey fringe that you can see are displaced by half a fringe interval when the number of photons goes from 0 to 1. So you see here the fringe pattern that you get when there is 0 photon in the cavity, and the one that you get when you have one photon. And if you set the interferometer to be at the top of a fringe with one photon number, you are at the bottom of the fringe for the other photon number. Which means that when the atom emerges from the cavity, you will find it in one state if there is 0 photon, and the other state if there is 1 photon, without having absorbed the photon. The photon is just manipulating the state of the atom without being lost. And this is a way we used to detect in a non-destructive way. The photons, you see here the birth, the life, and the death of a single photon in the cavity. And you see, for example, in the middle of this trace, that hundreds of atoms see the same photon. So it's completely different photoelectric effect. The photon is not destroyed, and it can just guide this atom in the upper state if there is 1 photon, and in the other state if there is 0 photon. So this is the basis for using this kind of system to store information in the field, and also if you have many atoms going across the cavity, you can entangle the atoms one by one in system and perform also some steps of quantum information. So this is the basis of what we call cavity QED experiments, and it has been recently generalized, recently means the last 20 years, to circuit QED with artificial atoms. And the last Nobel Prize of last October was given for that, for giving to you doing this kind of experiments with the hope one day to build a quantum computer, which is very far away from that, but using the same kind of physics, now not with real atoms, but with artificial atoms. The Rydberg atoms are not only interesting because they have a very strong coupling to microwave, they are also very interesting because they have a very strong coupling between themselves. For example, here we have focused double laser beams to trap 2 atoms at a fixed distance from each other. So they are trapped in their ground state by this radiative force, and then you try to excite them into a Rydberg state. So if you excite one atom, with the same laser you will not be able to excite the other one. Why? Because the atom into a Rydberg state is perturbing the energy level of the other, shifting them away from resonance, so that they cannot be, the same beam cannot be used, or 2 beams with the same spectrum cannot excite 2 atoms in the vicinity of each other. It's called dipole blockade effect. The dipole-dipole interaction blocks the interaction with the laser beam if one atom is already excited. So what happens now if you use a large beam, a beam which has a large waist and which can excite simultaneously the 2 atoms? What happens in this case is that you can only, this pair of atoms can only share one excitation. Either the first atom remains in the ground state and the other one is excited, or the opposite. So you have only one excitation shared evenly between the 2 atoms. And this state is an entangled state. It's a state which is not separated. The excitation is shared symmetrically between the 2. And you can start from there to entangle the atoms together and again play the game of quantum information. So this is now being developed in many, many labs, and you can prepare ensembles of atoms in a well-organized structure like this one. This is a signal which comes from the lab of Antoine Bourwais near Paris. And you can use the system to simulate what happens in paramagnetic or ferromagnetic or antiferromagnetic systems. The atom in the Rydberg state is like a spin up, and the atom in the ground state is like a spin down. And because of the blockade effect, the system is organized into different configurations. So quantum simulation allows to study phases of matter in different configurations. And I show you here only very quickly the latest results that you can get in this kind of experiment. You see here more than 6,000 cesium atoms on a lattice of optical tweezers. And you can interrogate each of these atoms, and it's a platform to simulate quantum matter at a larger and larger scale. And it's also a system which is promising for quantum metrology and quantum computing. very briefly, I want also to stress the fact that lasers have extended the notion of entanglement to very large distances. Back in the 1930s, Schrödinger had recognized that the entanglement is a very important feature of quantum physics. And in fact, entanglement is everywhere in quantum physics. Even the simplest of atoms, hydrogen, is entangled. In the ground state of hydrogen, the electron spin and the nuclear spin are entangled, and this ground state takes this form, spin up, spin down, minus, spin down, spin up. But the distance is of only 1 angstrom between two particles on average. Now, with lasers, you can propagate this entanglement to very large distances, and you can get pairs of entangled photons over kilometers. And this is, of course, the basis of quantum cryptography, quantum key distribution, and so on. So this is another direction. Now, I would like to conclude by quoting an experiment which has not yet given a positive result, but which is very promising. It's an experiment, a very precise experiment in spectroscopy, where one searches for new physics with ultra-precise spectroscopy. And the idea is to look for the electric dipole moment of the electron. According to the standard model of quantum physics, the electron is a sphere of electricity, exactly spherical, and it does not have a dipole moment. If the distribution of charges were slightly elliptical, for instance, there would be an electric dipole on top of the charge. And what the limits which are given by the standard model is that the electric dipole moment should be less than 10⁻36 electron centimeter, because the existence of such a dipole moment would be a violation of the time reversal symmetry, which is very well respected according to the standard model. But there are some models going beyond the standard models, so for example, supersymmetric theories which predict the existence of particles for which the time reversal will be violated by 3 or 4 order magnitude greater values, and it means that around 10⁻31 or 10⁻32 electron centimeters there is space for new physics, and so people are trying to find this, and this is something which is being done with spectroscopy. The idea is to look for a Ramsey fringe shift when you apply a huge electric field, either parallel or anti-parallel to the magnetic field. The magnetic field produces a Larmor precession of the electron spin, and if you have a small electric dipole moment, if you add the electric field in one direction or the other, you will shift a little bit its Larmor frequency. But you need a trick to do that, because the fields you can produce in the lab are much too small. So you have, in fact, to exploit an enhancement of the electric field inside a molecule having a very heavy nucleus. So you have some polar molecules with very heavy thallium nuclei, for instance. And there are 3 groups in Harvard, in Imperial College in London, and in Boulder, which are trying to make this measurement. And the record for the time being is 4 times 10⁻30 electron centimeter. It does not maybe mean a lot to you, but this is very small. In fact, if you blow up the electron to the size of the Earth, the difference between radius in one direction and the other would be only 0.1 nanometer. So you see that we are looking at the defect of sphericity of 1 part in 10 to the 17. So it's something very, very, very small, which has not been observed yet. But if you could observe that, finding an electron asymmetry at this level could be an evidence of new particles. For example, some particles which could be candidates for dark matter, with very important implications for quantum physics and maybe for cosmology. So this is the last experiment I wanted to show to you, but I would like, in conclusion, to relate this to what was being done in science 3 centuries ago. And this will bring us to what I said at the beginning, that it has something to do with South America, and I tried to explain. The passion for precision and the search for symmetry tree breaking was something which was a question which was raised at the French Academy of Sciences in the 18th century. The question, is the electron perfectly round, remains a question which was asked by Maupertuis at the Royal Academy of Sciences. Is the Earth exactly a sphere? And the answer to this question came from some interrogations which were based on time measurement. Huygens had beat the first clock, which was much less accurate than the one we have today, but it was the first scientific clock. And this clock was taken by an astronomer who went to Guyana, to South America, to make some astronomical measurements, to measure the parallax of Mars there, to compare with parallax of Mars in Paris, to make by triangulation known the distance from Paris, from Earth to Mars, so to have the size of the solar system, which was information which nobody had at that time. And what he remarked when he went there is that the pendulum was beating slower in Guyana than in Paris. And Huygens, who was following this closely, immediately understood that this might be due to the centrifugal force, to the fact that the equator, the point at the equator is going much faster than the point at the latitude of Paris, and this tends to expel the matter away from the Earth and decrease gravity, in fact. But if gravity is decreased, it means also maybe the masses which make up the Earth will be also slightly deformed, that the Earth will be bulging at the equator and not be a sphere, but a kind of oblate, like an orange. At the same time, another astronomer, Cassini, did not know, I made some measurement in France, and my hint is that the Earth is oblate like a lemon. So this was a question, and so Maupertuis said that this question had to be resolved by an experiment. You cannot just decide that you prefer one or the other, and so two expeditions were sent, one near the polar circle and the other one near the equator in Peru, in fact, and they made measurements, triangulation, a lot of measurements. They found indeed that Newton and Huygens were right and that the Earth is oblate. But you know, delta R over R is not 1 part in 10 to the 17th, it's about 1,000, so it's much less precise than what people are trying to do today, but still, what I want to emphasize is that the scientific method has not changed. To do research always taken time and money, and it was at that time, of course, much more adventurous than it is now. I summarize, you see here, this is the front page of the proceedings of the Royal Academy of Sciences, and translate the title, The Figure of the Earth Determined by the Gentlemen of the Royal Academy of Sciences who have measured the meridian degree at the polar circle. And there was a long description and details saying how they did the experiment and all the precautions they took to avoid systematic errors. And so I want to stress the common features with what we do now. First of all this is of course triggered by curiosity. You have a question you want to answer, and to answer the question you have to make an experiment, make an observation. You need to justify the utility. And at that time, Maupertuis said, this is not useless. Some people might believe that it's just a useless preoccupation of philosophers, but no, it's very important to know the size, the shape of the Earth for navigation. And this brings us to the GPS system also. So you have to justify, even if you do some basic science, to justify at least that one day it can be useful for something. You need to have the time to do it, to have the trust of your government, and this brings us back to the remarks that Juan Pablo did at the beginning of this meeting. You have also to use the latest optical technologies. In fact, Maupertuis used sextants which are sensitive to the position of stars with less than 1 arc second, so very, very modern devices which were just being developed for basic astronomy. You also need international cooperation. Celsius accompanied Maupertuis in that plan, and Bradley is the astronomer who discovered the aberration of stars. lent his sextant to Maupertuis, in spite of the fact that France and England were not in very good relationship at that time. And we have to evaluate systematic errors very seriously. And whereas 3 centuries later, laser make possible geodesical surveys of the Earth, which of course confirm Maupertuis' result, but with a much higher precision that was happened at that time. If you want to learn more about these stories, I have written a book which has been translated in Spanish, which tells many things about the history of light, going from Galileo telescope to the quantum strangeness. So I have inspired myself with this book to prepare this talk. There is also an article that I wrote to celebrate 100 years of quantum physics, which has been published in PRX Quantum this year. And in conclusion, I just want to share many points here. First of all, I hope I convinced you of the importance of lasers in basic science. Also the fact that lasers have inherited many tools which were invented in optics and in atomic physics in the pre-laser era. For example, Ramsey fringes, Stern-Gerlach experiment, optical pumping, all this was there before the laser. The passion for precision is at the heart of the scientific method, and other breakthrough can be expected in quantum physics, which might be important maybe even for cosmology. And of course all this also illustrates a deep connection between basic science and technology. And on the last slide, I just show you here that since 1964 you have had many Nobel Prizes in physics and chemistry which have used lasers to observe new phenomena, to make new discoveries. And this has been shared between physics and chemistry and astrophysics and condensed matter physics, a lot of domain of physics and chemistry research and biology. And this is not the end. I'm sure that there will be more in the future. And I stop at this point and I apologize for being very long. Thank you.
Okay, thank you very much for the very nice, interesting talk. So we have time for questions, comments. So raise your hand and go with mic. Hola.
Hello. Good afternoon. Well, first, thanks. It was an amazing class, an amazing lecture. I would like to ask you, because you didn't mention, there is no relationship between the lasers and the God particle, or all this kind of discoveries about this thing of the quantum mechanics?
No relation between what and what?
Well, between the lasers and the God particle, the boson Higgs. Boson. There is no relationship between those fields?
Of course, the Higgs boson is also a boson, but it's a different range of energies, and of course, when the Higgs particle decays, sometimes they put one signature is the ignition of photons, and so you have a coupling with the photon field. Maybe what I can say also is that there is some discovery which have a connection with supersymmetric particles or dark matter. Light would be used for that in this kind of experiment. Not in the accelerator experiment, but in this kind of experiment, light would be a signature of these events. So I think light will anyway be very important for future progress in basic knowledge.
Okay, thank you. Thank you.
Hello, and I want to ask if you think it could be some sort of discovery with lasers and all of that, with the theoretical particle about the gravity, the graviton, and if some experiment could, like LIGO or Virgo, discover that particle if it existed. Thank you.
I don't know. I think what you are alluding to is a connection between general relativity and quantum physics. The graviton would be, which is a particle which is the carrier of gravitational force, has not been discovered yet. It has not been effects directly linked to the existence of gravitons is still missing. But of course, electromagnetism and electrodynamics is a model for all this theory because it's the most precise up to now. And what will happen and what kind of connection will be made in the future to understand deeply this problem remains to be done. I think you need someone like Einstein to illuminate this physics. I don't think that artificial intelligence will help for that. Even if it's very useful to process data, I think you need some kind of imagination and creativity, which is, for the time being, eluding physicists.
Well, I don't know if this is right, but I wanted to ask if we could use lasers to communicate instead of radio waves with the, let's say with interplanetary probe like Voyagers or with a colony on Mars, because well, there's an issue with the radio waves, like they fade with the distance, and that's my question. Could we use lasers? Would that be much of a deal? Would that be expensive or what?
In fact, we use laser wave, the optical fibers which are under the ocean. They allow us to, all the computers of the world are linked by laser light and by a huge amount of information which is traveling at the speed of light everywhere, so it's being used in this way. And in quantum cryptography, you would do that too. You would be able to share secret keys which will allow us to code and decode messages without being spied upon, the possibility of spying. So there is a lot of research being done in that way. And all this relies on light, either laser light or single photons which are emitted by nonlinear optical processes which use lasers, in fact, to do that. And so it's, of course, microwaves are also very useful in a different context.
So could we use that in space?
What?
In space with the, let's say, probe like...
Yes, you can use laser interferometry in space, for example, the new antenna. There are projects to use gravitational wave antennas which will be based by the exchange of laser beams between satellites at large distances. And in fact, the first measurement using laser in space was done immediately after Armstrong walked on the moon in 1969. He left on the moon a reflector, a mirror, and immediately pulse lasers were aimed at this mirror, and the round trip between the Earth and this mirror reflected back on Earth gave the first precise measurement of the distance of the Earth to the moon, and this made possible many interesting tests of relativity in general and special relativity.
Thank you.
Hello. Hello. I have a question from here.
Well, yes.
You made quite a point to say we have
gotten a lot better with precision in the measurements. Do you think we are using lasers like close to the limit we can get, or do you think we can get more and more precise in the coming years?
Of course, if you look at the progress, which is a factor of 10 every 5 years, I think at some point we reach some limits to this move. But we are not yet at the limit, and I didn't have time to discuss that, but entanglement, the fact that you can detect with particles which have been entangled with each other, or on which you have been able to realize it's called squeezing, that is create non-classical state of light or matter, will allow us to make another progress of maybe 1 or 2 orders of magnitude, maybe in the precision of clocks or kind of measurement. So we are not yet at the limit. And for instance, the last experiment I described, they are hoping that they will be able to gain the sensitivity required to see something positive, a positive result in this experiment.
And I have more a question more like of science fiction. Do you think we could be able to use lasers to propel a spaceship like satellites or things like that? Like from the Earth shoot a laser to this?
No, I know that there have been some proposals to use this as a kind of solar light saving, but propagating at a very fast velocity, very light objects, may be able to carry a small camera. So if you can reach a velocity of, let's say, 1/10 of the speed of light on a camera which could send us back images, it might be interesting, but to go to the next star, it would take, even at the velocity which is 1/10 of the speed of light, take 40 years, and for the signal to come back to be 40 years. So we're talking with things which are already pushing reality very far. We are at time scales which are very, very long. I doubt it. I doubt that this project will work. The orders of magnitude, the power of the laser you need to do that is much too big.
Hello, here. Sir, here on the left.
Hello, good afternoon.
Here. Thanks a lot for the talk, it was amazing. One question, I see a lot of investment, private investment going to quantum computing, and from what I read, a lot of that in the US. I wanted to ask you from a basic science standpoint, how much in contact are you with that industry? What do you say about that? Are they using your advances?
Personally, I'm not in contact at all, but I know that there are many people who are. I know that there are a lot of startups which are working in this direction. I think that there is a lot of progress which has been made to manipulate and control a system made of larger and larger of particles, but we are still very far from a quantum computer because there is no decoherence is a big enemy, and the error correction codes which are being used now are not enough to reach the point where such a machine could be built. So I have doubts, and what I don't like is the overselling and the fact that people are claiming, since I started being interested in that, which means more than 30 years, people have always said, some people have always said that this quantum computer is around the corner, in 5 years and 10 years from now and so on, and the horizon is receding all the time. So at some point I think it might be counterproductive, but all the research which is being done here is very useful for other reasons. And for example, I'm amazed by the progress done by circuit QED and the experiment done with artificial superconducting junctions, which are quantum properties, and I'm sure there will be application of that for very sensitive probes, all kinds of possible applications.
Okay, good afternoon. My question was partially answered by your answer. My question was about the decoherence problem
on the quantum state and your opinion on the actual state of the technology and the possibility to overcome that problem, the inequality problem.
I think I have already answered. I think there have been a lot of progress, for example, to observe quantum effect in mesoscopic systems, to look at quantum effect in membranes which are vibrating, which are made of a huge number of atoms, or cantilevers, or solid objects which in some respect are macroscopic because there are a huge number of atoms in them, and you already see some quantum effect in the systems. So your boundaries between the quantum and the classical world are pushed back, but it's not enough. What you have to do is to be able to control that on a system which will have a huge degree of freedom, that is a huge number of degrees of freedom, many particles, and it becomes increasingly difficult to do that. To have a collective quantum effect is obvious. Bose-Einstein condensate, you have a big number of particles and they are in a quantum state, but you don't have many quantum states. It's just a single quantum state, only two or three of them. What you need to be the quantum computer is to have n particles that you can manipulate one by one, and n being huge, and without decoherence, and this is very, very hard. I don't say it's impossible, there is no impossibility in principle, but it becomes technologically very hard. And there have been in the past examples of situations where just because of technological difficulties, some projects had to be abandoned. I don't know what will happen with quantum computing, but I'm sure that in the way to go there, a lot of interesting things will be discovered.